Welcome, Physics 30. This is the Unit 3B, Part 1, Kinetic Energy booklet. In this booklet, we'll be looking at defining and providing examples of kinetic energy and solving problems involving kinetic energy. So it's going to be a shorter booklet than usual. So energy is the mover of matter. 6 examples of energy: energy of motion, chemical energy, heat energy, electrical energy, light energy, nuclear energy. Those are all forms of energy. Kinetic energy, of course, is this one here, involving energy of motion. Work and energy are related in that the work is equal to a change in energy. So in order to have a change in energy happening, work must have been done on an object. So if we take a look at 5 characteristics of energy, energy is transferred from one object to another when work is done. So if you are lifting a box, you're transferring energy from your body to the object. Energy has many interchangeable forms. So we could go from moving energy to stored energy, etc. Energy transformations occur when energy goes from one form to another. Energy can be stored to do work later, for example, a battery. And energy is conserved. There's no loss of energy. It's simply transformed into something else, usually in terms of heat or friction. And over in the duotang, in the energy section, there's basically kind of a flow chart here illustrating energy. So object has rest mass energy. Stored energy, of course, is potential energy. We'll look at that in the last booklet. And in this booklet, of course, moving energy is kinetic energy. And yeah, so and this question here kind of deals with the same thing there. I'm not sure why I asked it twice. So kinetic energy, energy an object has as it moves. So moving energy, so of course it's dependent upon how fast it's moving, its speed. It's also dependent upon how massive it is. So the relationship here, kinetic energy, or EK, is 1/2 mv squared, where m is mass in kilograms, v is speed in meters per second, and that would give us joules as an overall result. So we get here mass meters squared per second squared. That is equivalent to a joule. Vector or scalar, it's a scalar quantity, but of course, just like work, it can be gained or lost. So if the kinetic energy is increasing, it is considered positive in that it gained energy. Or if it's the object lost kinetic energy, it would have a negative energy value, meaning that it was lost, of course. Okay, if we look at some questions here involving that. What is the kinetic energy of a 1/2 kilogram ball thrown at 30 meters per second? So of course we know m, we know v. So EK equals 1/2 mv squared. Mass is 0.5. V is 30. So don't forget to square it here, of course. So square first, then multiply. 225 joules. And the next one here, B. What is the kinetic energy of a 25-gram bullet traveling at 3,600 kilometers per hour? So a couple of unit manipulations here. We have to change grams into kilograms. So 1 kilogram over 1,000 grams. And we get 25 grams equaling decimal 0.250 kilograms. Or simply divide by 1,000. Now, earlier on in one of the previous units, an easy way to go from kilometers per hour to meters per second would be to divide by 3.6. Or, of course, if we want to do the individual manipulations, 1 kilometer is 1,000 meters. 1 hour is 60 minutes. 1 minute is 60 seconds. Either way, we get 1,000 meters per second is what that bullet would be traveling. So we have our correct units: 1/2 mv squared, 1/2 times the mass of 0.0250 multiplied by 1,000 squared. So that leaves you with 13,000 joules. What is the mass of an object traveling at 20 meters per second with a kinetic energy of 4,000 joules? So we're manipulating this equation to solve for mass. So here first multiply each side by 2. Then we're left at just simply 2ek, 2 times kinetic energy equals mv squared, divided by v squared to isolate mass. And we get m is equal to 2ek over v squared. So just substitute our values into there. 2 times our kinetic energy of 4,000 divided by 20 squared. Now recall that if I had left energy instead of joules, left it as kilogram meter squared per second squared, we would get everything canceling out here and be left with kilograms. Next, what is the speed of a 1.5 kilogram rock falling with a kinetic energy of 48 joules? So solving for v, multiply each side by 2, and we get that, 2ek equals mv squared. Divide each side by m, and we get 2ek over m equals v squared. Then of course to solve for v, you'd have to take the square root of that. So substitute the numbers in, square root of 2 times our kinetic energy of 48 divided by 1.5, 8.0 meters per second. A half kilogram rubber ball is thrown in the air at a height of 20 meters above the ground. It's traveling 15 meters per second. What is the ball's kinetic energy? So of course we know the kilograms, we know the speed, so there we have it, 56 joules. How much work is done to accelerate a 150 kilogram motorbike from 10 meters per second to 20 meters per second? So here we're dealing with work. And earlier I mentioned in order for work to be done, a change of energy must happen. And of course the change in energy is involving a change in kinetic energy. We're going from 10 meters per second to 20 meters per second. So work is equal to change in energy. In our case here, the change in energy is kinetic energy. So to find that change, we have some final energy minus some initial energy. And of course, the difference between final and initial is the speeds. Final speed, initial speed. So 1/2 mvf squared minus 1/2 mvi squared. So if we take a look at that, our final speed, or initial speed is 10, final speed is 20. So there we have it. We'll have 30,000 minus 7,500, 22,500 joules. It's relatively easy. If you're dealing with work, we have to deal with change in energy there. Okay, that's it. So we just have the kinetic energy vocab term. Energy due to the motion of an object, Ek equals 1/2 mv squared, dependent upon mass and as well speed. Okay, there you have it. So that is the second last booklet from the energy section dealing with kinetic energy. See you again.